Hey, welcome to The Explainer. Ever stop to think about the science that's kind of hiding in plain sight? I mean, it's everywhere. In the coffee you drink, the vast oceans, and even on the icy roads in winter. Today, we're going to pull back the curtain on this hidden world and dive into the chemistry of solutions.
So, it all kicks off with a question you've probably asked yourself. It's freezing outside, right? But then you see someone scatter salt on an icy sidewalk, and almost like magic, the ice starts to melt. How does that even work? Why does simple salt seem to beat the cold? Well, the answer is just a fantastic piece of chemistry, and we're going to break it all down.
Okay, so to get to the bottom of this mystery, first things first, we've got to get a handle on what a solution actually is. Think of it like a recipe with two main ingredients. First, you've got your solute. That's the stuff being dissolved. So in our example, that's the salt. Then you've got the solvent, which is the stuff doing the dissolving. In this case, water. You put them together and bam, you've got a saltwater solution. Now, the official term here is a homogeneous mixture. That fancy word homogeneous is really key. It just means the mixture is so perfectly and evenly blended that the individual solute particles become totally invisible. They've mixed in so completely, it's happening right down at the molecular level. But here's where it gets really interesting. It's not just about the act of mixing. The amount of solute you toss in there is what gives a solution its real superpowers. And this brings us to the crucial idea of concentration. Concentration is really just a measure of how crowded the solvent is with solute particles. If you put just a little bit of salt in a whole lot of water, that's what we call a dilute solution. But if you dump in a ton of salt, it becomes a concentrated solution. And it's this crowdedness that really starts to change things in a big way. And here is the main takeaway. When you add a solute to a solvent, you're doing way more than just changing its taste. You are fundamentally changing its physical properties, things like the temperature at which it freezes or boils. This simple act has some seriously powerful consequences. So, what's the scientific principle behind all this? It's got a great name, the colligative effect. And this is the secret behind our whole salty road mystery. A colligative property is a property that depends on just one thing, the number of solute particles you've added. That's it. It doesn't care what they are, could be salt, could be sugar, doesn't matter. The solvents only cares about the quantity. It really is like a party, right? It's not who shows up that changes the feel of the room. It's how many people are packed inside. So how does this play out with freezing? Well, for water to become ice, its molecules need to line up in a very neat, organized crystal formation. But when you add solute particles like salt, they're like tiny little obstacles. They just get in the way, physically blocking the water molecules from locking together. And to overcome all that interference, the solution now needs to get much, much colder than 0 degrees Celsius before it can finally freeze. And boom, there's the answer to our first question. The salt on the road lowers the freezing point of the water on it, which means it stays liquid at temperatures where it would normally be a sheet of ice. Actually, it can drop that freezing point all the way down to about -9 Celsius. And this exact same principle is used to de-ice airplanes. They just use a different solute, ethylene glycol, to get the job done. And what's really cool is that this same idea works in reverse when it comes to boiling. Those same solute particles that block freezing also make it harder for water molecules to escape the surface and turn into steam. So that means you have to pump more heat into salt water to get it to boil, up to around 102 degrees Celsius instead of the usual 100. We call this boiling point elevation. This ability to mess with a liquid's physical properties is incredibly powerful. But changing freezing and boiling points, that's just scratching the surface. So let's look at another one of these colligative properties, one that nature uses to keep things in balance, and that we've engineered to solve one of the biggest challenges humanity faces. This property is called osmosis. You can think of it as nature's way of trying to even things out. So if you've got two solutions separated by a special kind of filter, a semi-permeable membrane, water will naturally flow from the less concentrated side to the more concentrated side. It's literally trying to dilute the stronger solution to make both sides equal. So that's the way nature wants to go. But what if we could fight that? What if we could actually reverse the flow? Could we push water from the more concentrated side, say from salty ocean water, back to the less concentrated side, leaving all that salt behind? Turns out we can. The process is perfectly named reverse osmosis. By applying a whole lot of external pressure to the salt water, we can overpower that natural tendency. The pressure literally squeezes the pure water molecules through the membrane's tiny pores, while the bigger salt particles are simply too large to fit through, so they get left behind. And this is not just some neat lab trick. Reverse osmosis is the core technology that powers huge desalination plants all across the planet. It's a truly life-saving application of solution chemistry, turning the salty seas into fresh, clean drinking water for millions upon millions of people. And the science just keeps getting better. As this quote from our source material points out, researchers are now developing incredible new membranes made from carbon nanotubes. These can make the whole process way more efficient. We're talking about slashing energy costs by up to 75%. It's an amazing glimpse into where this technology is headed. So, from melting ice on our roads to creating fresh water from the ocean, the chemistry of solutions is this powerful, invisible force all around us. It really makes you wonder, doesn't it? What other invisible chemistry is quietly shaping our world every single day? Thanks for tuning in.